Hello, everyone. This is Can Unal, and I'll be talking about the spin effects in accretion and jets and its reflection on the fundamental plane relation. And using this spin modified version of this fundamental plane, we will derive some properties of the ultralight particles via superradiance. So this talk is mainly based on the two papers I had with Fabio Paciucci and Avilöb. So fundamental plane is mainly the correlation, a plane equation in log base of the radio luminosity and the X-ray and the mass. In the heart, there are two main physical variables when you describe these, the mass and the mass accretion rate. But we realize that there are AGNs whose radio power is even 3 orders of magnitude different, even if their masses and X-ray powers are almost same. So we thought that maybe there's another variable which we suggest spin, which also exists in this fundamental plane relation. So the effects of spin on accretion and the jet power is well known for some time. So now let's remember some and then derive a couple new results. So first part is the radiation efficiency. Like the particles who are outer edges of the accretion disk come in and then they radiate through their process. And typically the radiation efficiency is set by the innermost stable circular orbit. And this ISCO orbit comes closer and closer to the horizon as the spin of the black hole grows, such that this gravitational potential energy is transferred more into radiation for the accretion disk who are around fastly spinning black holes. And this efficiency is expressed in many years ago by Bardeen in the following way. The spin has also effects on the power, jet power, the outflowing energy. This is introduced by this Blandford and Znajek famous paper. It depends on both the spin parameter, its square, also the horizon size and the magnetic field threading that horizon. When the spin is low, the main contribution to this effect is just spin, quadratic order in spin. But when the spin goes to moderate and larger values, the jet power becomes much more strongly depend on the spin values higher than the quadratic order, and we will see that now. So starting with the magnetorotational instability, which connects the behavior of the particles and the magnetic field strength, and then adding up like the information from the specific angular momentum of the particles and the just number conservation, one can end up with a semi-classical result that we have about the strength of the magnetic field threading the horizon and combining the horizon size with change of the horizon with the spin and the strength of the magnetic field with the spin and all the spin dependent quantities, one ends up with the following result. So as you see, for low spin values, really jet power is quadratically almost proportional with the horizon spin. However, for moderate and large spin values, the dependence is much stronger. And remarkably, in the really high values of the spin, this goes to almost the 6th power of the horizon angular frequency. And remarkably, some simulations conducted many years ago find a similar functional dependence in the higher spin values. So which is very motivating. Now, we would like to, so we understood a bit the effects of spin on both Blandford, Znajek and jet power, and also on the accretion power. Now, let's incorporate this information into the fundamental plane relation, such that turn it into a spin modified, spin incorporated fundamental plane relation scaling. So this is what we have. Earlier, we didn't have these parts of the spin contributions, but now this is the general form of the spin modified fundamental plane relation. And now let's try to understand if you could be able to explain the scattering scatters from the earlier original fundamental plane relation with the spin. So we define some delta parameter which is indicating the scatter such that this, when delta is 0, this is the definition of the fundamental plane relation. And then these deviations are spin dependent functions. So here, green dots are indicating the data points, and the blue dots are corresponding to the predictions from the fundamental plane. And for these AGNs, the spin is relatively robustly determined such that we could plug these spin values into our prediction, and then we could see, also including the spin error, we could see how the theory, how the spin modified fundamental plane relation predicts the data points. And we see that there's a really strong statistical evidence that with this incorporating the spin information, these predictions are following the data points much better than this standard fundamental plane relation. So you can imagine the following way. If the spin has no role at all, it should be just a random reshuffling. Some places should be going close to the data points, some points should be away from it. But here in almost all the cases, the prediction follows the data pretty good way. So another way of seeing this is the following. So this is the original fundamental plane relation. And then the scattering, the variant, the standard deviation is about 1, but when we incorporate the spin of these 10 AGNs and then define our axis in such way, we realize that all these data points shrink and these scatter values drop considerably. And we found that statistically significant improvement in our results. So which shows a strong motivation for this prediction. Now we would like to add one more, go one more step beyond. So we would like to use OIII lines instead of X-ray, such that we get rid of the uncertainties in the X-ray luminosity, because there are still debate on the origin of the X-ray sources, and there are more uncertainties. Since OIII lines are non-relativistic, we consider that this could be also a good probe for the M dot as well, M dot and mixture with the M as well. So we do the similar analysis, but instead of X-ray, now we have OIII lines. And we also consider various errors that could be affecting the our predictions, let's say the radio power, such as the Lorentz factor, viewing angle, and errors in the luminosity measurements. And then we derive some lower bounds on a number of AGNs. And then we would like to use these lower spin bounds as constraints on ultralight particles. So now with this calculation, we turned a spin modified fundamental plane as a spin estimator. And these are the observed variables. And with the information of the boost factor and the viewing angle, you can go to always the source frame and then extract out the spin information. So before going to the constraints and physical properties of the ultralight particles, I would like to just say a few words about superradiance phenomena. It is the instability of the Kerr black hole to the light perturbations. So when there is an incoming wave, a fast spinning Kerr black hole enhances these ultralight particles, and then the spin energy, rotation energy of the Kerr black hole is reduced to produce these light particles. So, which means if you see some particles, if you see that black holes who are spinning fast, which means this superradiance phenomena has not happened. If there are no self or external interactions of these ultralight particles, then you can rule out these and relevant parameter space of these light particles. But of course, it's a possibility that these guys could have some external or self interactions which prevents these particles from entering the superradiance regime. If you assume there is no self or external interactions and superradiance phenomena is there, since we don't observe the low spinning, we observe these highly spinning black holes, we could say that no such particles exist. Here the red, with the assumption that, of course, again, there is no interaction. So only gravitational one. So these red rectangles are corresponding to the AGNs whose spins are measured with conventional techniques such as the reflection method and iron line position. And these green ones are predicted by this feeding the information to the spin modified plane that I just discussed a minute ago and extracting out the spin information, lower bound for that. So spin value is higher than this derived lower bound. And then as you see, we probe actually the largest range of these ultralight particles thanks to this new relation that we have, this our new spin estimator, which is remarkable. You can follow the same procedure for the vector spin 1 particles. Since their interaction rate, superradiance phenomena rate, is much faster than the scalar particles, you can probe a larger region of the vector particles, and you can do the same analysis for the spin 2 tensor particles. Again, this blue region is the measured spin values measured with conventional techniques, and the purple color here is corresponding to the spin values predicted by the spin modified plane, actually from the lower bounds that we derived. Now we could learn more about these particles the following way. Assume this superradiance phenomenon is prevented by some kind of self-interaction. So if self-interaction is preventing these guys to enter the superradiance instability regime, then maybe there is some self-interaction, and self-interaction is usually indicated by this axion decay constant, and it is inversely proportional with the axion decay constant. So we could imagine there is some degree of self-interaction which prevents these particles to enter the superradiance regime, which corresponds to an upper bound on F axion, such that F axion should be smaller than some values, upper bounds, so that the self-interaction is strong enough for prevention of the superradiance. And we end up with this plot. Here again, these rainbow colors are corresponding to spin modified fundamental plane prediction, and the other ones are standard conventional spin measurement values, and altogether they're probing more than almost 4 decades actually. And then final step, we could ask ourselves the following question. These ultralight guys are really possibly important ingredient of our dark sector, and they could be, of course, the dark matter as well. Combining the information from the mass and the axion decay constant, one could infer their typical energy density and what fraction of dark matter they could constitute, and then again put a constraint on these values. So it seems, as you see from the plot, in the range of 10 to the minus 21 electron volts to 10 to the minus 17 electron volts, ultralight particles could only form about 10% of the dark matter. And of course, depending on the regime, for example, 10 to the minus 19 to 10 to the minus 17, they could be at most a percent of the dark matter. And these bounds are valid for a single species. If you have more than one such ultralight species, these bounds can relax some degree. So these are the conclusions, and I would like to thank for your attention.